Good afternoon. I, Sandhya Bhardwaj from IIMT College of Engineering, Greater Noida. Today, I'll discuss the topic that's semiconductor diode. Here is the first slide. That in this we include introduction of diodes, electrical property of solids, semiconductors, PN junctions, semiconductor diode, spatial purpose resistor or a spatial purpose diode circuits. This course adopts a top-down approach to the subject, and so far we have taken a black box view of active component such as op-amp. In this, now time to look inside the box. Then we'll start by looking at diode and semiconductors. Then progress to transistor. After that, we will look at more detailed aspects of circuit design. Then what is diode? Diode is a switching element, an ideal diode passing electricity in one direction, but not the other. So we can also say that the diode is unidirectional. And here it IV characteristics, I current, V voltage with respect to each other. Here the graphical representation, and here the diode circuit symbol. Like positive charge, the end is anode, and negative, the end is cathode. And current will flow only in forward direction. Then the application of diode is in rectification. The example below show a half wave rectifier. In half wave rectifier, a sinusoidal wave that it can conclude or it can accept only positive cycle, not the negative cycle. So as shown in figure, here in practice, no real diode has ideal characteristic, but semiconductor PN junction make good diodes. So to understand such devices, we need to look at some property of materials. Now we are talking about electrical property of solids. The conductors, as example, copper or aluminum, have a cloud of free electrons at all temperature above absolute zero. So if an electric field is applied, electron will flow, causing an electric current. And we are talking about the insulator. Insulator is like example polythene. So in this, electrons are tightly bound to atom, so few can break free to conduct electricity. In terms of chemistry, that we can also say that the nucleus and the orbit has trivalent or tetravalent. In this, the first orbit, the atoms are tightly bounded, so it cannot break or it cannot free to conduct electricity. Now the semiconductor, example silicon or germanium. At very low temperature, these have the properties of insulator. As the materials warms up, some electrons break free and can move about, and it takes on the properties of a conductor. However, semiconductors have several properties that make them distinct from conductor and insulator. In terms of energy band diagram, we can also say that in conductor, the valence band and conduction band are overlapped to each other. But in insulator, the forbidden energy gap is very high, so they cannot move valence band to conduction band. But in semiconductor, the forbidden energy gap is so small, so the electrons can move valence band to conduction band when we increase the temperature. Because at initial or 0 degree temperature, the semiconductor can also behave as an insulator. Semiconductor. That pure semiconductor thermal vibration result in some bonds being broken, generating free electrons which move about. And in pure semiconductor, these leave behind holes which accept electrons from the adjacent atom and therefore also move about. Again, electrons are negatively charged carriers and holes are positively charged carriers. At room temperatures, there are few charge carriers. Like pure semiconductor are poor conductors. This is intrinsic conduction. Then what is doping? Doping is the addition of small amount of impurity drastically affect its properties. Doping some material from an excess of electrons and produce an N-type semiconductor. Some material form an excess of holes and produces a P-type semiconductor. Both N-type and P-type material have much greater conductivity than pure semiconductor. This is extrinsic conduction. For example, as we say that for the pure gold, we cannot make ornament. So we can make a alloy, or it is also called as doping. The dominant charge carrier in a doped semiconductor, for example, electrons in N-type material are called majority charge carriers. Other type are minority charge carrier. For example, in P-type semiconductor, the holes are majority charge carrier and the electrons are minority charge carrier. Vice versa, N-type opposite to P-type, that electrons are majority charge carriers and holes are minority charge carrier. The overall doped material is electrically neutral. That mobile positive charge shown in figure, the wound negative charge, and it is in the N-type semiconductor, mobile negative charges, the bound positive charges. Then what is PN junction? Basically the junction, the term when two or three or many to make together form a junction. When P-type and N-type material are joined, this forms a PN junction. When P-type and N-type material are joined to each other and forms a PN junction. In PN junction, majority charge carriers on each side diffuse across the junction, where they combine with and remove also charge carrier of the opposite polarity. Hence, around the junction, there are few free charge carriers and we have a depletion layer, also called a space charge layer. The diffusion of positive charge in one direction and negative charge in the other produces a charge imbalance. This results in a potential barrier across the junction. As shown in figure, the diffusion of positive charge in one direction and the negative charge in the other produces a charge imbalance. That is called potential barrier across the junction. Then what is potential barrier and how it is work in forward wise and reverse wise? The potential barrier, the barrier oppose the flow of majority. Barrier that oppose the flow of majority charge carriers and only a small number have enough energy to surmount it. This generates a small diffusion current. The barrier encourages the flow of minority carriers and any that come close to it will be swept over. This generates a small drift current. For an isolated junction, these two currents must balance each other So the net current is 0. If we are talking about forward wise, if the p-type side is made positive means holes, with respect to the n-type side means electrons, side the height of the barrier is reduced. More majority charge carriers have sufficient energy to surmount it. The diffusion current therefore increases while the drift current remain the same. There is thus a net current flow across the junction which increases with the applied voltage. If we are talking about the reverse bias, in the reverse bias, the p-type side is made of negative, while in forward bias, the p-type side is made of positive. The p-type side is made of negative with respect to the n side. The height of the barrier is increased. Potential barrier increased just because of reverse bias. The number of majority charge carriers that have sufficient energy to surmount it. It rapidly decreases. The diffusion current therefore vanishes while the drift current remains the same. Thus, the only current is a small leakage current caused by the approximately constant, either drift current. The leakage current is usually negligible. Current in a PN junction as shown in figure. Here some type of diagram and graphical representation about the P type and N type as it is a forward wise and reverse wise, as we are also talk about the isolated junction. So here are some graphical representation for many isolated junction, forward wise, reverse wise, forward and reverse current. PN junction current is given approximately by I is equals to IS, where E is the electronic charge, V is the applied voltage, K is Boltzmann constant, T is absolute temperature, and eta is a constant in the range 1 to 2 determined by the junction material. So we can raise the eta from 1 to 2 only. The most purpose, we can assume eta is equals to 1. Thus, here some graphical representation of I is equals to Is exponential EV upon KT minus 1 at room temperature. E upon KT is equivalent to 40 volt. And the minus 1 is shows saturation current or reverse wise or reverse saturation current. Semiconductor diode, the forward and reverse current. Here graphical representation, then the how semiconductor is behave in forward wise and reverse wise in terms of IV characteristic, applied current or voltage. Then what is silicon diode? Silicon diode generally have a turn-on voltage of about 0.5 volt. Generally have a conduction voltage of about 0.7 volt. Silicon diodes have a breakdown voltage that depend on their construction. Perhaps 75 volt for a small signal diode or 400 volt for a power device. Have a maximum current that depends on their construction. That it is like 100 milliampere for a small signal diode or many amperes for a power device. Turn on and breakdown voltage for a silicon device. And how a silicon device work in forward wise and reverse wise? In reverse wise, there is a breakdown voltage. We are denoted VBR, and in the forward wise voltage, the value is 0.5 volt. As we showed, as shown in figure, straight line approximation to silicon diode characteristics. It is for silicon only. A special purpose diode, the special purpose diodes is light emitting diode or LED. Now the Zener diode, Zener diodes use the relatively constant reverse breakdown voltage to produce a voltage reference. Here R is a load and the symbol is Zener diode. V0 is output and V voltage for input. The breakdown voltage is called the Zener voltage, which is denoted by Vz. Output voltage of circuit shown in equal to Vz despite variation in input voltage V. A resistor is used to limit the current in the diode. Like Schottky diode formed by the junction between a layer of metal, example aluminum, and a semiconductor. Schottky diode action relies only on majority charge carriers, and it is much faster in operation than the PN junction. And it has a low forward voltage drop of about 0.25 volt. Then it is also used in the design of high-speed logic gates. Same as tunnel diode. Tunnel diode high doping levels produce a very thin depletion layer which permit tunneling of charge carriers. And if we have a thin depletion layer, here it is efficiency is increased, result in characteristic with a negative resistance region. And tunnel diode used in high frequency oscillator where they can be used to cancel out resistance in passive components. Now again, Vector diodes. Vector diodes, a reverse bias diode, has two conducting regions separated by an insulating depletion region like a capacitor. So this structure resembles a capacitor. Variation in the reverse bias voltage change the width of the depletion layer and hence the capacitance. Vector diode produce a voltage dependent capacitor. These are used in applications such as automatic tuning circuits. Now, a diode circuit is half wave rectifier. Half wave rectifier, as we talked earlier, like it can consider only positive cycle. So, peak output voltage is equal to the peak input voltage minus the conduction voltage of the diode. Reservoir capacitor used to produce a steadier output, means constant output. Again, full wave rectifier in term of bridge rectifier uses a diode bridge reduce the time for which the capacitor has to maintain the output voltage and thus reduce the ripple voltage. In the bridge rectifier, two diode can conduct electricity in one time. The signal rectifier used to demodulate full amplitude modulated signal, full AM, also known as an envelope detector. Full AM signal, here it is a sinusoidal, the signal is demodulated. So then signal rectifier found in a wide range of radio receiver from crystal set to super heterodines. Signal clamping, a simple form of signal conditioning. Signal clamping circuits limit the exertion of the voltage waveform, and it can use a combination of signal and Zener diodes. Now again, catch diode. Catch diode used when something inductive loads. The back EMF, large back EMF can cause problems such as arcing the switches. Catch diode provides a low impedance path across the inductor to dissipate the stored energy. Catch diode applied voltage reverse biases the diode, which therefore has no effect. When the voltage is removed, the back EMF forward bias the diode which when conducts. Here are the some key points of the introduction of semiconductor diode. Like diode allow current to flow in only one direction. So we can also say that diode is unidirectional. If we are talk about the transistor like bipolar junction transistor, field effect transistor, metal oxide semiconductor, field effect transistor, that is MOSFET. So the bipolar junction transistor is bidirectional. It can conduct electricity in both the directions. Again, at low temperatures, semiconductors act like insulator. As with respect to energy band diagram, we can also say that the forbidden energy gap between valence band and conduction band is small, but at low temperature or 0 degree temperature, the electron have not enough energy to move from valence band to conduction band. So we have to raise the temperature or increase the temperature, then the electrons move from valence band to conduction band. So when electron moves to valence to conduction, they create a hole. At high temperature, they begin to conduct. Like if we increase the temperature, we are talking about the semiconductor because diode is made of semiconductor material. So 0 degree temperature, it is act as an insulator. If we increase the temperature or at high temperature, they begin to conduct electricity. Because when we raise the temperature, the electron get the enough energy to move from valence band to conduction band. Doping of semiconductor lead to the production of p-type and n-type material. That is intrinsic or extrinsic. A junction between p-type and n-type semiconductor has the properties of diode. Silicon semiconductor diode approximate the behavior of ideal diode, but have a conduction voltage of about 0.7 volt. Germanium is 0.3 volt. So silicon semiconductor diodes approximate the behavior of ideal diode. There are also a wide range of special purpose diode. Special purpose diode like tunnel diode, Schottky diode, Zener diode, catch diode, also shown in figure, and you can also say these are the also wide range of special purpose. Why this is special? Because they will work in reverse wise. Or in the earlier session or in the earlier slide, we can also say that the diode is conduct current in only forward wise or only in one direction. So these are the some special purpose diodes. Diodes are used in a range of application. Many application has diode get the maximum efficiency or they will work much faster. And if we are talking about the doping of semiconductor leads to the production of p-type and n-type material. Then we can make a alloy of this, or in pure semiconductor, we add on a impurity on it. So they can improve their behavior or they can improve their efficiency. So the doping process is very important for that. A junction between p-type and n-type semiconductor has properties of a diode. If they have the different property, so p-type and n-type semiconductor has met and make a junction. That is p-n junction. That p in the p-type, the majority charge carriers are holes, and the n-type, the majority charge carriers are electron. Because if electron moves from one to another or valence to conduction, they can create a hole or a vacant space. That is known as in silicon semiconductor diode approximate the behavior of ideal diode but have a conduction voltage of 0.7 volt in terms of silicon, or it will behave, and behavior of the silicon semiconductor diode is like a ideal diode, and in germanium it is 0.3. So Germanium semiconductor diode is not a ideal diode, because in comparatively in earlier time we can use germanium, then we can find out the silicon has a great property with compared to silicon or germanium. So these are also a wide range of special purpose diode. Diodes are used in a many range of application. And if we talk about the bipolar junction type, bipolar junction transistor, FET, MOSFET. So initially we are used germanium. After that we are discovered silicon. Then the compound like two or more or one or more. That is gallium arsenide. So the property of is modified in one to another or with respect to another. So here are the some key points that I have already discussed. So thank you. Thank you so much for that.
What is it?